Hello guys, this is Dr. Maharjan. I hope you guys are safe and doing well. So in this video lecture, I'll be talking about the topics that you will need for your lab, virtual lab, and the homework problem. So this is where we stopped last time. So we introduce this new topic, transistors and operational amplifiers, and we briefly mention the basic functions of transistors. The two major applications of transistor are one as a voltage amplifier. As you can see in this animation, a small voltage gets amplified because of transistor action, and the second most important application is a digital on and off switch, a non-mechanical digital switch. A transistor can be turned on and off by applying a gate voltage, as you can see, and those on and off switches work as a logic gates, as you can see here, and which we will learn at the end of the semester a little bit. So one such amplifier input impedance of the amplifier, where the higher the better, because then spend most of it will isolate topic studying operational source. It will operational amplifiers are constructed. On the other hand, integrated circuit technology. This particular 741 chip impedance of the amplifier operational. The lower the better, because then it can transfer almost all signals to the 30 transistors inside. So this is this is block diagram, constructed symbol of a voltage integrated circuit amplifier. This is where we stopped last time. So today's lecture, I will get started with an important. So first, op-amps were first used operational amplifier during the analog computing. Analog computers, analog computers will be, and it is also called operational amplifier because besides amplifying property, it can also do many mathematical operations. So that would for example, adding, subtracting, differentiation, integration, something like that, which we will study as we move on. And so that's why it is called operational amplifier. And the most important point is operational amplifier has a very input impedance, which is very good, and a very high gain. And this is how you construct an operational amplifier. And this is a symbol. This is a chip layout with all the pin connections. So it's a op-amp that we'll be using in our lab. Has an 8-pin chip, but most of the time we'll just be using actually 5 pins. So number 2, 3, 4, 6, and 7. Here's the OpAmp symbol. Okay, this is the symbol for our OpAmp operational amplifier. So it has basically 3 terminals. In symbol, you just need 3 terminals. So 2 input terminals and 1 output. So this first one is V plus input. So this is also called non-inverting input, because if you apply a signal to be amplified like this, output will be in phase. Output will be amplified signal but in phase. And the second type of input is called inverting input, because if you apply tiny signal like that, so the output will be inverted by 180 degree out of phase. Okay, so that's why this V minus input of the op-amp is called inverting input, because the signal output will get 180 degree out of phase. Okay, so this is the symbol. But in most of our calculation, even this symbol can be now reduced to just a triangular shape with just 3 inputs, 3 terminals. One is V plus, which is the non-inverting input, right? And the next is inverting input, and next is V out. You just need these three terminals for OpAmp for most of the calculations. Okay. And now next, let me show you the main golden rules. It's so-called golden rules to for most of our OpAmp calculations. So here's the OpAmp golden rules. Okay. So OpAmp, if you want to make OpAmp as a stable amplifying voltage amplifier, uh, you need a negative feedback. This box shown here is called negative feedback because it will bring the output voltage, some of the output voltage, to the inverting input, so that it will make this V plus and V minus inputs forced to be equal. Because if V plus and V minus are not equal, right, not equal, then you get saturation. You get the output will be saturated like this, right? Because output, you will have output like this, so you will only see within that, because the output voltage can't be greater than your supply voltage. Let's say this. Since the op-amp gain is very high, 10 to the power 5 to 10 to the power 9, a small difference in this differential voltage can lead to the saturation. So you can't make it as a stable amplifier. So that's why in most of the cases, if you want to use op-amp as a voltage amplifier, you need a negative feedback. So here's the golden rule for op-amp. So if ideal amplifier is configured in negative feedback, so input draws no current first of all, so it doesn't draw any current, and V plus is equal to V minus. Inputs are forced to be equal. Otherwise, what happens? Otherwise, you'll get saturation like this, and you can't use it as an amplifier. So this negative feedback to the V minus, right, is very important. And then to solve the circuit problem, just apply KVL, nodal analysis, KCL, to find the voltage and currents and so in the next slides, now I'm going to show you some applications of OpAmp, how you use OpAmp as voltage amplifier, as adder, subtractor, something like that. So here's an example of inverting OpAmp, inverting operational amplifier. So in inverting operational amplifier, you connect the circuit like this. You need two resistors like this, and this works as R1 works as a negative feedback. And then so we'll be calculating the output voltage in terms of this external resistors. So we'll be calculating so is amplification factor. So for example, so I can apply KCL, Kirchhoff's current law, at this node V minus at inverting input. So as you can see, there are only two currents. So I1 plus I2 is equal to 0, right? But since V plus is connected to the ground, right? So that will force V minus also equal to 0, right? Because why? Because in OpAmp, from the OpAmp golden rule, we know that V plus has to be equal to V minus, right, for a stable OpAmp. So because of this, since V plus is connected to the ground, V minus has to be ground, right? And then you can apply now our regular nodal analysis. So I1 is V input, right? This is the input signal voltage, minus V negative divided by R2. That's I2 actually. Let me see. Plus I1 is V out minus V negative divided by R1 is equal to 0, right? So but since Vi is negative, V negative is 0, right? This is forced to 0, so V negative is 0. This is also called virtual ground. You will hear this word actually, virtual ground, because since V plus is connected to ground, this is indirectly connected to ground, so it's also called virtual ground. So then this is 0, V input divided by R2 plus V output divided by R1 is equal to 0, right? So then V out over R1 is negative V input divided by R2. So V out divided by V in, which is we call voltage gain, is equal to negative R1 over R2. So this ratio is we call voltage gain, is negative R1 over R2. Okay, this is called voltage gain. And as you can clearly see right there, since there's a negative sign, the input and output will be out of phase. So if this is V in, your output will be, it will be amplified depending on amplification factor, right? But it will be like this. It will be 100-degree out of phase. That's why it is called inverting OpAmp configuration. Okay, so that's how you can calculate the amplification factor of OpAmp in this configuration. And the most beneficial part of OpAmp, using OpAmp as an amplifier, is now the voltage gain completely depends on the external factors, because you can choose these resistors, right? So the voltage, how much voltage gain you want, is completely up to you by choosing these resistances. It doesn't depend on its intrinsic property. So that's the best part of using OpAmp. So so this is how the input and output look like. So this is the input, like I already explained, right? So output will be 100-degree out of phase. Okay. And one more to be careful when you use amplifier, OpAmp as amplifier, is that OpAmp has some limitation. So this is the frequency response of the OpAmp, right? So this is the most important part. So for any OpAmp, the gain and bandwidth product will be always almost constant. So for example, so if you choose the gain as 10, let's say, so this is the gain, same as AV, right? You will have more bandwidth. So bandwidth, how do you calculate the bandwidth? So first you have to calculate FC. FC is the initial voltage divided by square root of 2, right? So, and this is called gain bandwidth product, right? But if you configure the OpAmp with higher gain, then you lose the bandwidth, as you can clearly see. If you go higher gain, you lose the bandwidth. So when you, depending on your application, right, when you configure any OpAmp, you have to be careful how much bandwidth you need and how much gain you need. So depending on the gain, you have some limited bandwidth. All right. So the next amplifier configuration is non-inverting OpAmp configuration, right? So in non-inverting, so this is how you configure, the OpAmp as non-inverting. So you apply the negative feedback through this voltage divider circuit. So you still need negative feedback, but through the voltage divider, something like that. And you apply the input signal to the non-inverting inputs, V plus. That's why it is called non-inverting, because you're applying the signal to the V plus. And let's figure out the, let's do some math and calculate the gain, the voltage gain of this configuration. So again, starting, so now your V minus, right, your V plus is V in, because that's where you apply the signal input. And so however, V minus is the voltage here, right? The V minus, which is the input to the inverting input, is the voltage across R2, right? Because this is just a voltage divider, so which is given by so R2, because we are looking at the voltage across R2 divided by R1 plus R2. I'm just using the voltage divider, simple voltage divider, times the output voltage, whatever total voltage you have. The total voltage is the output voltage, right? But from amplifier OpAmp rule, uh, says V plus has to be equal to V minus. Remember, this is the golden rule for any OpAmp. So then set them equal. So V plus is equal to V minus. V plus is V in. V negative is R2 divided by R1 plus R2 times V out. And what you need is V out divided by V in, because that's your voltage gain, is now R1 plus R2 divided by R2, and this we call the voltage gain. A of V is then R1 plus divided by R2 plus 1, right? And that's the formula for the voltage gain in non-inverting configuration. Okay, so that's how you solve. So, and you can clearly see, right, the it's called non-inverting because uh, if this is the input signal, right here, the output will be exactly in phase. The amplified output will be exactly in phase. So that's why it is called non-inverting input. And it will be something like that. Okay. So these are all done on lecture slide. So here's an example of using OpAmp as an audio amplifier. So in this configuration, it works as non-inverting input configuration. So here's the OpAmp. So these are the plus VCC. This is the power supply for the OpAmp. Remember, OpAmp needs both positive and negative polarity voltages with respect to ground. So here you connect the microphone. The microphone converts your audio signal sound energy to electrical signal, which needs to be amplified many times before you feed it to the output device, such as speaker, right? So here's the question: what's the gain of this audio amplifier? And we have just derived the formula for, non-inverting gain, and non-inverting gain is 1 plus R1 over R2, right? So here is 1 plus, so R1, this is R1, 100k, 1k, so it's 101 times, its amplification factor is 101. So that's the first question. It's pretty easy, right? Just use the formula. So now second question is, so if the audio signal to amplify has a frequency range from 300 Hz to 3.4 kilohertz, that's where the most of our audio signal frequency spectrum will be within this range. So, and if the chip, this OpAmp chip, has a gain bandwidth product of 600 kilohertz, let's say, right? Can you use this circuit as to amplify the audio signal? So that's the question. So in order to figure that out, whether you can use this configuration or not, with at this gain, you need to do show gain bandwidth product, as you know. So it says this chip, this OpAmp has gain bandwidth product, right? Gain times bandwidth product as 600 kilohertz. So our gain is 101, which is about 100, is 600 kilohertz. So I forgot bandwidth. So your bandwidth, the bandwidth you have to amplify this signal is, for this chip, is 600 kilohertz divided by, so I'm just gonna call 100 and round it to 100. So you still have 6 kilohertz, of bandwidth. So you have enough bandwidth, right? So for this chip, so you can amplify up to 6 kilohertz, right? Uh, and it says your audio signal will be within this range, so you can very easily use this as amplification because you have enough bandwidth, 6 kilohertz. So that's how you do some calculation when you design amplifier. Okay, let's move on. Now the OpAmp in this configuration is also called unity gain OpAmp, unity gain amplifier, because in unity gain amplifier you're just making the voltage gain as 1, and I'll tell you in a second what's the use of this actually. So you just put a jumper from output to the inverting input, and you apply signal to the non-inverting input. And if you configure OpAmp like this, it's called unity gain OpAmp. And why is that? Because here now we know that Vi is equal to V naught. Why? Because V plus is where you apply signal, input signal. V out, right, is feedback to V in exactly without any resistors. So, but V plus is V minus. That's the golden rule for OpAmp. So that means output voltage is equal to input voltage. So output divided by input is 1. So voltage gain is 1. So why do you need a unity amplifier? So since OpAmp has very high input impedance, as you know, tens of mega ohms, and that's where it is used for isolation. So for example, if you just apply, this is the source, any source, and as you know, any source has some internal resistance, right? Because none of the sources are perfect. And if you apply this input to any your circuitry, so it loses some voltage. So it internally loses some voltage like this. This is the loss. But if you isolate this input source, input source to your rest of the circuit with unity gain, OpAmp, then you can transfer almost all the voltage to your circuitry. So your output voltage will be exactly equal to the source voltage, and the voltage you're applying to your circuitry will be exactly equal to the source voltage, so without any loss. Because why? Because it has very high input impedance. Right, you can well isolate any circuitry like that. That's the main use of unity gain amplifier.